Hey, it's AP Chemistry time. Today we're looking at isomers. So let's first talk about what in the heck is an isomer. If there are two or more compounds that have the same molecular formula but a different arrangement of atoms, then we consider those to be isomers of one another. The arrangement of atoms in the compound could result in different chemical or physical properties, and so isomers are distinguishable one from another because they would react in different ways, or they would have different boiling points and different melting points and so on. So we know that isomers have the same molecular formula. But an isomer where the bonds are in different places, atoms are bonded in different locations, are called structural isomers. But you could also have the atoms in the same bond, but they would be arranged in a different geometry, so those are stereoisomers. Among the structural isomers, you could have coordination isomers, or you could have linkage isomers where the bonds are in different places, and I'll show you some examples of those. As for stereoisomers, you could have geometric isomers where the atoms are in a different location in the molecule, or optical isomers where they would rotate plane polarized light in different ways. First, let's look at coordination isomers. They would differ in the ligands that are directly bonded to the metal in order to form the positively charged complex ion. For instance, you could have the water that's bonded to the chromium, and then the chloride is attracted to this positive ion. Or you could have one chlorine that's also bonded to the chromium in place of one of the waters, so it still has a 2+ charge overall, and then these chlorides are attracted to it, and then the water embedded in its molecular structure is still involved. So it's exactly the same atoms involved, they're just rearranged in a different crystal pattern. Linkage isomerism occurs when a particular ligand coordinates to a metal in two different ways. Usually we would see this with a nitrite or thiocyanate because these ions have so many different locations of high electron density. That's our key here. This high electron density is going to have an attraction for a metal ion, right? So in our cobalt ion, the nitrite can react so that the nitrogen is bonding to the cobalt, or you can have the oxygen part of the nitrite bonding to the cobalt instead. These are linkage isomers, and these are a pretty rare type of isomer to find. In geometric isomerism, this would be a result where atoms are arranged differently, but the same bonds are present. And often these are referred to as cis or trans. So notice in the first example with platinum, the chlorines are located next to one another. Cis would be when the chloride ions are on the same side, or whatever ligands there are. When they're arranged on the same side of the atom, that's considered the cis type of structure. But trans is when they line up across from one another. So the chlorine ions line up across, and this tends to be more stable because it puts these highly electronegative atoms farther apart from one another. Remember how the chlorine would have 3 lone pairs of electrons. If we can spread those out farther away, we're going to stabilize the structure. This is where they get that prefix trans fat. That's referring to the locations of atoms arranged around double bonds in a fat molecule. Optical isomers are also called enantiomers. Enantiomers are mirror images that cannot be superimposed on each other. For instance, your hands can be folded across because they're mirror images, but they cannot be superimposed on one another because you have a definite right and left. So they're mirror images, but you can't just put one on top of the other. That's what an enantiomer is like. Molecules or ions that are not superimposable on the mirror images are said to be isomers of one another. And they rotate optical light in two different ways. For example, your right and left hand on a mirror can't be superimposed. But if you had methane or carbon tetrachloride, then those are interchangeable. They look the same. If you look on page 964 in your textbook, you'll see some other examples of enantiomers. So if you're asked about a change in physical or chemical properties based on molecules that appear to be almost the same, consider maybe there's an isomer that you're overlooking.